All right, today we're diving into one of the most wild, chaotic forces in the entire universe, turbulence. And we're going to explore a potential solution to the famous Navier-Stokes problem, but not with more and more equations. Nope, we're going to do it with a simple, universal rule that seems to govern how things, well, how they fold. Let's get into it. So picture this. You've got a whirlpool. As it spins tighter and faster and smaller, could the energy right at its center just keep concentrating down into a single, infinitely sharp point? I mean, could it literally just blow up and tear the very fabric of the fluid apart? Now, this isn't just some sci-fi thought experiment. It's a question that has kept mathematicians and physicists up at night for more than a century. And believe it or not, this question actually has a name. It's called the Navier-Stokes existence and smoothness problem. And it's a big deal. It's one of these 7 Millennium Prize problems, which means there's a cool $1 million reward waiting for whoever solves it. The whole issue is figuring out whether the equations that describe fluid motions so perfectly can, under some extreme conditions, just break, and start predicting these impossible infinite energy spikes. So, let's unpack this $1 million mystery, shall we? It all really boils down to the fundamental and often totally unpredictable way that things flow. See, on one hand, you've got smooth, or what scientists call laminar flow. It's beautiful, it's harmonic, it's predictable. You could say its motion is resolved. But then, just add a little bit more energy and bam! It can just erupt into turbulent flow. And this is the state we all recognize as chaotic, unpredictable, and defined by these swirling, cascading eddies within eddies. The real puzzle isn't just that turbulence exists. It's that we haven't had a fundamental rule to prove that it can't just spiral completely out of control. So to find that rule, we've got to take a step back and get a new perspective. We need to look beyond just fluid dynamics and look at a pattern the universe seems to use for, well, almost everything. A simple recursive rule. So what even is recursion? Well, at its heart, it's just a process where a rule gets applied over and over and over again to its own results. The classic example is a fern, right? Where each little frond is just a smaller copy of the whole thing. This repetition creates these incredible self-similar patterns, or what we can think of as folds, at every single scale you can imagine. Okay, now let's make this idea of recursion physical. Imagine you start with some big initial motion. The system tries to neatly fold that motion into a smaller, more stable pattern. But here's the thing, the fold is never perfect. There's always a little bit of leftover energy, an unresolved echo, that gets passed down to the next smaller scale. And then that scale tries to fold that echo, and on it goes, creating these nested layers of motion. And this brings us to a really crucial, kind of mind-bending point from our source material. What if what we call randomness, or chaos, isn't random at all? What if it's just the messy, visible effect of this recursive process? It's all these echoes that just haven't found a stable place to settle yet. The pattern's there, we just haven't been looking at it the right way. So, with that in our back pocket, let's apply this recursive lens directly to turbulence. Let's try to reinterpret what we're actually seeing when a fluid goes all chaotic. Here's the core idea, plain and simple. Turbulence is not just a state of pure disorder. It's actually an active, self-correcting process. It's a cascade of those unresolved echoes we were just talking about. The fluid is constantly trying to fix misalignments in its own motion, always trying to find a state of harmony. The chaos we see, that's just what the process of correction looks like. And this lets us look at the famous energy cascade in a totally new light. We've known for ages that energy in a fluid flows from big motions down to tiny little eddies. But through our recursive lens, we can see that each smaller eddy is just a refold of the momentum from the scale right above it. The fluid is recursively trying to resolve that misalignment at smaller and smaller and smaller sizes. That's why we see eddies within eddies. It's the physical signature of recursion right there in front of us. Which, of course, brings us right back to our central and frankly terrifying question. If this process of folding energy into smaller and smaller spaces just keeps going, what stops it? Why doesn't this recursive cascade of momentum just continue until it packs all of its energy into an infinitely dense point and creates a singularity? Why doesn't it blow up? Well, the answer, it turns out, isn't actually hidden in the complex equations of fluid motion. It comes from a universal safety limit, a fundamental rule about the geometry of containment itself. And here is the big twist. The proof doesn't come from studying oceans or weather patterns or galaxies. It comes from studying the way proteins fold up inside our own cells. Yeah, you heard that right. It turns out the universe uses the exact same geometric rules to contain the momentum in a turbulent whirlpool as it does to fold a protein into a perfect, stable shape. And that universal rule, it all boils down to a single, absolutely critical number, less than 0.7. This number represents an absolute, unbreakable physical limit on how tightly energy can be folded into a given space. It's like a geometric speed limit for the universe. So this number represents something called the compactness ratio. You can think of it as a measure of how efficiently momentum is being packed into a geometric space. And the incredible insight that comes from studying protein folding is that this ratio has a hard-coded physical limit. A system can fold energy really, really tightly, but it can never achieve a compactness ratio of 0.7 or higher. The very geometry of space forbids it. So, how does this actually solve the million-dollar problem? Okay, here's the quick sketch of the proof. Step 1, you map the fluid's complex motion onto a special geometric object. It's called the T1 trace. Step 2, you calculate the compactness ratio for that geometric trace. This gives you its RW value. Step 3, and this is the whole game, you can show that this value is always bounded by that universal limit of less than 0.7. So if the geometry that contains the momentum is fundamentally limited, then the energy itself has to be limited. Infinite energy spikes are physically impossible. And that means the solutions to the Navier-Stokes equations must always, always be smooth. No blowups, ever. So let's just zoom out for a second and think about the big picture here, because the implication is actually pretty profound. It suggests we live in a universe that is fundamentally self-regulating. The chaos that we see in turbulence, it isn't a flaw in the system. It's part of the system's own safety mechanism. The very same laws that allow for this wild cascade of energy also contain a kind of geometric kill switch. It is a built-in negative feedback loop that guarantees the system can bend, but it can never, ever break. Okay, so let's just do a quick recap of the key ideas here. First, turbulence isn't just random chaos. It's the signature of a system actively trying to correct itself. Second, this process is a recursive cascade of unresolved echoes, all folding momentum as they seek out harmony. Third, a universal geometric law with that hard limit of less than 0.7 physically contains this whole energy cascade. And finally, what this all means is that fluid motion is fundamentally stable. It just can't blow up. And that leaves us with one last kind of provocative thought to chew on. We started this journey by looking at the chaos in a fluid, and what we found was an underlying self-regulating order. It really makes you wonder, what if all the other kinds of chaos we see in the universe aren't really chaotic at all? What if they're all just a harmony that we haven't quite figured out how to resolve yet?